Hello, Lisa. Can you hear me clearly?
Hi, Mo. Yes, I can hear you. Can you hear me?
Yeah, beautiful. How are you today?
I'm doing great. How about you?
Awesome, awesome. I'm doing very well. Thank you very much for asking. Are you connected to the
It's a
session
pleasure.
from
So,
Australia
I'm
or?
sharing my video to you. Could you please confirm if you can see me clearly?
Yeah, here we go. I can see you. And let me just share my video as well. Can you see me?
I can see you now.
Okay,
I can see you
beautiful.
now, Dr. Mo. Can you see me?
Yeah, beautiful. You are clear here. I can hear
Uh,
you very well,
I
and
don't
I can
hear
see you.
you. Do you happen to be on mute?
Sorry, what did you say?
Dr. Mo, are you talking at the moment? Because I don't hear anything. Just making sure everything goes well.
Yeah, everything is okay. I can hear you clearly. I can see you as well. Just a question: will the
I
attendees
heard you
see us,
earlier.
or uh, can I ask a question, Lisa? Can I ask a question, Lisa? Lisa, can you hear me? Can you hear me, Lisa? Hello. Okay, beautiful, Derek. Thanks very much for saying that. I can't see Lisa actually at the moment. Okay, beautiful. Thanks very much for the feedback. Beautiful. Um, I'm not pretty sure. I should ask Lisa whether I need to have my um, voice on only or just have the share the video as well. Lisa, can I ask you a question? I'm not pretty sure. Should I just keep my video on or just turn it up to make sure that everyone uh, hears me clearly? Yeah. I agree with Hezron because sometimes having the video on can interrupt my voice. So I'll turn the video off to make sure that everyone can hear me clearly and we don't have any interruption during the session. Beautiful. We have now 32 attendees in this session, and then we're going to start within 10 minutes.
Hi, Dr. Mo. Are you there? Can you hear me?
Yes, I am. Yes, I am. I can hear you clearly. Yes, I am. Can you hear me, Lisa? I clearly hear you, Lisa, but I reckon you can't. If you hear me, just let me know that you hear me as well, because I'm receiving feedbacks from attendees saying that they hear me clearly, but I don't receive any feedbacks from you. Beautiful. Thanks for the feedback, guys. Thank you. So I'm just suspecting that Lisa cannot hear me clearly because I'm not receiving any feedbacks from Lisa. Okay, beautiful. Thank you, Paco. It's great to see that everyone hears me clearly. The only problem is that I don't have any feedbacks from Lisa. So I hope that he will get online and then we can start within 3 minutes.
Hi, everyone. We will be starting our webinar shortly in 3 minutes. Thank you so much for joining.
Awesome. Okay, we have just only 1 minute to go, and then Lisa will start the session. It's awesome. We have about 58 people attendees. I would like to say hi to Riley, my friend at EIT, who's done a lot of work to get this session started and done.
Hey guys, can you hear and see me now?
Yeah.
You can give me a thumbs up, a smiley, or a yes or an okay in the chat. Thank you so much. All right, everyone, it's 2:30 and let us now start our session. So everyone kindly go to your settings part, just go to your, just click on the purple X mark, the white X mark with a purple background in your lower right corner of your screen and go to notification settings and please uncheck all the boxes in there so that you wouldn't see any notifications, no distractions during our webinar. Just make sure all the boxes are not selected. All right. So I hope everything's good with your notifications. If you have questions, you can just let me know in the chat box. And let's start. So by the way, my name is Lisa Magad. I'm one of the course advisors at EIT, and I'm going to host this webinar. And our webinar is about the effects of harmonics on distribution transformer efficiency. And it will be presented by Dr. Muhammad Saleh Naderi, and he is one of our lecturers and one of the electric power systems experts that are connected with EIT. And you can call him Mo or Dr. Mo.
Hello. Hi,
And
Lisa.
also, after this presentation, after this webinar, we can send you a copy of the PDF slides and a video recording. Usually it will be sent to you via email in 1 to 2 business days. And if you don't receive it still after that, kindly have a look at your junk email. Maybe it went there. And you can also request for a free certificate of attendance. And later on, we will be sharing a link on how to request for your certificate. And usually we'll be sending it to you within the next 1 to 2 business days once you have filled out the form. So let's start with getting to know EIT first. So we are one of the few engineering specialist school in the world, and we have a variety of courses to choose from short-term courses like professional certificate courses, diplomas, advanced diplomas, and we also have bachelor's degree, master's degree, and even a Doctor of Engineering degree, and some undergraduate and graduate certificate courses. And we are also a school that offers industry-oriented programs. So our programs are designed by experts in the engineering industry. That is because we would like to keep our curriculum updated with the latest engineering trends and developments as well. And we are also accredited by world-class accreditation organizations. So aside from our accreditation by the Australian government, we also have programs that are also recognized under the 3 international engineering accords, such as the Dublin Accord, the Washington Accord, and the Sydney Accord by Engineers Australia. And of course, our lecturers are also industry experienced, just like Dr. Mo, and we select them very carefully. They should be people who are experts in the industry, because we would like our students to have, as much as possible, a real life experience or exposed to real life scenarios in the engineering world. And we also have a unique delivery model. So we have a blended approach. So aside from our pool of expert lecturers, we also provide you the dedicated learning support officers. So each course will have a dedicated learning support officer, and that person is the go-to person of the student whenever the student has concerns or need any guidance or help during his study. And of course, we make it sure that we have state-of-the-art technologies, such as our hands-on workshops, our remote laboratories, and our simulation softwares as well. So I'll hand over this presentation now to Dr. Mohammed Saleh Naderi. Again, he is one of our lecturers at EIT, and he is also an electric power systems expert. Dr. Mo?
Thank you very
This
much
is
for the
yours now.
introduction, Lisa.
Thank you.
Thank you very much for the introduction. Just before we get started again, because we have about 98 people attendees in this session, can I ask, please let me know that for the lights check that you hear me clearly? That give me a thumb up or a yes in the checkbox, and then we get started. Okay. Beautiful, beautiful. Thank you very much for your feedback. And I remember my classes that I had a couple of years ago when I had about 460 students in my class, and now here I'm seeing around 100 people attending this session. And thank you very much for attending this session. Okay, we are recording as well. Right. Just again, another question before I get started to have an idea about what are the attendees actually in the field. Are you mainly students or utility engineers, or you're doing both? Can you just write in the check box saying that you're a student or an engineer working in utility or somewhere? Engineers in practice, beautiful. Beautiful, Malcolm. Okay. Okay, we have a combination of engineers and the industry students. Thank you very much for that. Okay, my presentation today is based on a study that we did. We conducted the study a couple of years ago. I could say that it was about 2006, 2007, based on a survey that we saw on EIA website. EIA is actually an Energy Information Administration, which is a governmental entity in the US. The survey result was saying that the people, the household in in the US are using increasingly using LED lamps in their houses, especially owner-occupied homes, more than renter-occupied homes. So we conducted the study to see that what would be the effect of using different types of lamps on the distribution transformers and the efficiency of the transformers, and how using harmonic generating lamps can derate the transformers in distribution systems. So we conducted this study, and in a laboratory base, actually we conducted experimental tests, and we did some simulations using Matlab to do the verifications. So today I'm going to present the results of that study here, and then just before we get started, because I'm going to see the effect of using different types of lamps in the transformers and the efficiency, do you have any idea what percentage of US households can use are using LEDs or incandescent lamps or CFLs? Any ideas about that? No, okay. Let me tell you the survey results from EIA. According to the EIA, the number of US homes using LED as one of the main lighting options increased from 4% in 2015 to 47% in 2020. It's amazing, isn't it? And this information comes from the latest residential energy consumption survey, which is called REX, completed in 2020 and 21 and published in 2022. Actually, in 2006, when we conducted this study, there was another survey out from the EIA saying that the number of households that were using LED lamps in their houses were in the US. So LED lamps were used were increased from 4% of homes to 47% of homes. And incandescent lamps or halogen lamps, they decreased from 31% of homes to 15% of homes. So this was showing us a trend saying that people are moving from incandescent lamps, the traditional incandescent lamps, towards the energy-saving lamps like LEDs and CFLs. So what would be the impact of these? These are energy-saving lamps because energy was important. Energy is always important. Energy has been important actually from 2 decades ago. But what would be the effect of using or increasing number of LED and CFLs on the transformers efficiency? When you look at the many studies have been conducted on I'm focusing on different aspects of using LEDs and CFLs, but in that time we didn't have too many studies saying focused on the energy aspect of using LEDs and CFLs. Energy, you can hear these days many social media and websites talking about energy efficiency, energy management, energy transition, actually moving from fossil fueled power systems to renewable powered power systems. So this is a trend. This has started already about 5 to 10 years ago. And we will have the higher penetration rate of renewables in our power system and higher penetration rate of harmonic generating loads actually in our systems. So one of the products or consumables that we are using in our houses are lamps. We have 4 different types of typical lamps that is normally used in our households. We traditionally used incandescent lamps, and then we moved them to fluorescent lamps, and then compact fluorescent lamps, we call them CFLs, and then light emitted diode or LED lamps. So these are four different types of lamps that we usually use in our houses. What is important is that they are energy saving lamps when we move on to the LEDs and CFLs, but at the same time they are harmonic generating lamps as well. When we're saying they are generating harmonics, it means that they are generating losses in our systems. And we are having increasing amount of losses in cables and transformers, which will affect their thermal capacity and maximum loading. Some people, some researchers believe that the transformation's efficiency should be improved by making changes in the design and manufacturing procedures, while some other looking at the problem from a network perspective and believe that improvements should be made by the efficient operation of the equipment. So some people are utility. Yeah, I can hear you.
Hi,
Do you want
sorry,
to interrupt me?
wanting to check if you can you control the slides?
Yeah, I will move on to the slides in 2 minutes time,
No
and
worries.
I'll talk about the agenda. Yeah, thank you very much.
Thank you.
So what I'm trying at the moment to say, give an introduction about different types of lamps and energy efficiency and transformer efficiency, and then move on to the agenda. I'm on the first part, the welcome and the introduction, and then I'll talk about the effects of harmonics on transformer efficiency. Then we talk about transformer loading capability, and we do have 2 case studies on lamps and transformer losses and rating. One was conducted experimentally in a laboratory, and the second study was actually a simulation when using Matlab. And then I'll talk about the results, so experimental results and simulation results, and then at the end we come up with the conclusions and see, and I'll take your questions at the end of the session. So to start with, I was talking about different types of lamps and energy transformer efficiency. As I said, some people and some scholars are saying that it's important to make changes in the design and manufacturing procedures. Some others looking at the problem from the network perspective and saying that we should make improvements in the efficient operation of the equipment. When we're talking about the harmonics, we are saying that if we have only the fundamental current, which is denoted by I1, then the entire current, the total current will be I1, which is definitely is less than or equal to the cases when we have harmonic components in the current. So because we do have harmonic components in currents, then we will have some added losses in transformers. So when we have lamps, different kinds of equipment in our houses, like, you are now hearing about digitalization. So we do have a lot of digitalized things in our houses. We're using laptops, we're using iPads, tablets, and different types of mobiles and lamps, different types of lamps. So they are generating harmonics. When they are generating harmonics, it means that we are drawing more current from transformers. So as I said before, we are increasing the losses in transformers, which will affect eventually their thermal capacity and maximum loading. In this next slide, I'm showing you that if we have only the active power and reactive power, which can give us the apparent power S, we don't have any distortions, we don't have any harmonics, which is denoted by D. you can see that when we have harmonics, they increase the apparent power from this green vector to that yellow vector. The absolute value of the apparent power that is needed to deliver the same amount of active power to our households will be increased. So we need to have more installed capacity in our system to deliver the same amount of power actually to the households. So rather than having S squared equal to P squared plus Q squared, we will have S squared, which is the apparent power, equal to P squared plus Q squared plus D squared. It means that if you want to have the same, if you want to deliver or supply the same amount of P to your customers, you need to have more installed capacity in the system. Now, before I move on to the next slide, let me talk about the different types of lamps and their modeling. As I said, we have been moving from incandescent lamps into CFLs and then LEDs. To have a general information about when CFL and LED lights came out, I would say that LEDs have been around for more than half a century. In fact, the viable working version of LED technology first came out in 1962. And in terms of CFLs, CFL was actually invented in 1976 by Edward Hammer, which was an engineer who was an engineer with General Electric in response to the oil crisis in 1973. So they have been around for many years, but the penetration rate of these lamps in our houses has started from about 2 decades ago. In 2001, 2002, we had a number of households moving from incandescent lamps into LEDs and CFLs. There was one simple reason for that, because there was a reason for replacing incandescent lamps with other types. That was the wattage required for tungsten filament used in incandescent lamp was almost about 4 to 5 times more than the wattage needed by CFLs, for instance. So CFLs and LEDs are considered energy-saving lamps, but at the same time, as I said, there are harmonic generating lamps as well. Now, when we're trying to find out how they are affecting our transformers, the first thing to know is that how we model these lamps, energy-saving, so-called energy-saving lamps. So to model these lamps, usually CFLs are represented by a nonlinear resistor and a nonlinear reactor, and LED lamps are represented by a diode curve, which are not accurate, especially in the case of LED lamp, because there is a complementary AC circuit behind these lamps. And these models, these conventional models, are not considering that complementary AC circuit. So what would be the best model for these lamps? The experimental samples of current is actually the main, is in the time and frequency domains for both lamps, can provide more pragmatic and complete model. You know, in CFLs, we do have an inductive ballast for the normal operation and a starting capacitor to ignite the gas in the lamp. So, and in the LEDs, LED is actually a semiconductor device that emits infrared or visible light when charged with an electric current. A single LED is a low voltage solid state device, and cannot be directly actually operated in household AC current without circuitry to control the current flow through the lamp. So we do have a capacitive reactance and a Zener diode that makes we can use the LEDs 230 volt household AC current. So we do have a complementary AC circuits behind LEDs and CFLs. So we need to have a pragmatic and complete model of these lamps, and then we can study how they affect our transformers efficiency. We have done in our we have actually executed this kind of experiments to find an accurate model of these lamps. You will see the results soon. So if you look at the different studies on academic researches on lamps, we do have a number of studies in 2000, between 2000 between 2000 and 2010. There is a lot of actually papers published in prestigious international conferences and journal outlets, which discuss different aspects of harmonics, how they affect transformers, cables, and one of them was actually our study. So we do have a number of standards, actually international standards and Australian standards as well. One of them is Australian standard 61000, which is electromagnetic compatibility. It's on the electromagnetic compatibility. The limits for harmonic current emissions. It was actually published in 2007. There is another standard, an Australian standard, which is a 2279.2-1991. Can I ask you guys turn up their microphones? If you have any questions, you can just put in the chat box, and I'll get back to you at the appropriate time. Thank you very much for that. So we do have other standards, Australian standards as well. One of them is 61000.4.13, which is on electromagnetic compatibility, testing and measurement techniques. 0.4.7 is on EMC as well, which is a general guide to harmonics and interharmonics measurements and instrumentation for power supply systems and equipment connected thereto. So we do have a number of standards, Australian standards. They get revised as well. We do have new versions of these standards available. If you guys need to have a look at these standards, you can get actually a good insight into the different aspects of harmonics and how you can do measurements based on these standards. We still have a few guys having their microphones on. Can I ask these guys to turn their microphones off to avoid any interruptions or distractions to the attendees, please? In terms of international standards, we do have IEEE standards and IEC standards. The latest version of IEEE 519 has been published in 2014. The earlier version was published in 1992. It is IEEE recommended practices and requirements for harmonic control and electric power systems. We do have another IEC standard or IEEE standard 1159, which was published first in 1995. The latest version was published actually in 2008, which is about the recommended practice for monitoring electric power quality. We do have another IEEE standard, which is C57.110, which was published in 1998. The latest version actually came out in 2018, which is again the recommended practice for establishing transformer capability when supplying non-sinusoidal load currents. So, we do have, if you want to get again good insight into what would be the best practice to do research on harmonics and how they affect the transformers and cables, you can have a look at these standards. So when we're looking at the transformer losses, we do have two types of losses. We can imagine two types of actually losses. One is the effect of voltage harmonics, and the other losses are due to having current harmonics. So as I said, when we have harmonic components, it means that we are drawing more current from a transformer to supply the same demand. So in terms of the voltage harmonics, it's actually no load. The red one here, it's actually the no load power. So first, I'll talk about the voltage harmonics and then the effective voltage harmonics. What would be the formula to assess the effective voltage harmonics? And then we'll, okay. I can take your questions at the end of the session because we have about 15 minutes to go to just finalize my presentation, and I'll take your questions later on. So we do have P and no load power, which is due to voltage losses, harmonics, and we do have PDC, PEC, and POSL, which are owing to having current harmonics. So nonlinear loads, as I said, can cause additional losses in the transformers, and we have non-sinusoidal conditions at that time when we do have those harmonics in the system. P&L is actually affected by transformer voltage excitation, and other terms are by distorted transformer current. So basically, when we have an AC current applied to a primary winding of a transformer, it generates actually magnetic field in the core, which induces voltage in the secondary winding. According to Faraday's law, when a conductor surrounds a time-varying magnetic field in the core, it can induce a voltage onto the conductor. This induced voltage consequently will result in an AC flowing through the AC current flowing through the secondary windings conductors. So which can be shown, that induced voltage can be shown like this expression, epsilon is the induced voltage, which equals N times d phi over dt. And in the frequency domain, we can write it like epsilon h equals to j omega h ph for h from 1 to n. We do have losses owing to the currents, effect of current harmonics, actually. Again, nonlinear loads can cause additional losses in the associated distribution transformers. We do have effects of harmonics on DC losses, which is proportional to I squared, and eddy current power, eddy current losses we do have in the conductors, which is proportional to IH squared and H squared. H is actually the number of harmonic. When we're saying the second harmonic, H is 2. For the third harmonic, H is 3. And we do have effects of other stray losses, which is proportional to IH squared and is proportional to H to the power 0.8. I'm not going through the details of these formula there. These are coming from the standards that I mentioned earlier. So what we know is that those losses, all the current losses, are proportional to the I squared. So which is very important. So when we look at the IEEE standard, it gives a harmonic loss factor, which is expressed like this here. And we do have winding losses that can be normalized to either fundamental or the RMS current. So if we just normalize the winding losses, we can write it like this expression here, which can be found in IEEE standards and IEC standard that I mentioned. We have a copy-paste of, almost copy-paste of these formulas in our Australian standards as well. So Now, if you look at the international standards, they recommend a method to determine the loading capability of transformers subjected to non-sinusoidal load currents, especially IEEE 519 that I said the latest version came out in 2014. It's based on actually the condition that per unit value of non-sinusoidal current will cause the same hotspot losses as the rated sinusoidal current. And it gives us this expression for the maximum current that we can have in per unit system. To reduce transformer eddy current losses, we need to decrease the Z-mid parameter, which is very important in the transformers if you look at the standards. So the loading capability of transformers is affected by the harmonics, and it has been standardized. You can find in different international standards and our Australian standards as well. I'll move on to, at this stage, I'll move on to the experiments that we did, we conducted in a laboratory in Australia a couple of years ago. This we had a voltage source, which was a household 230 volt voltage. We sampled the current through using a current meter, and we had a power quality analyzer which sampled their voltages. And then we measured the voltage and current. So we wanted to have the best model for CFLs and LEDs in our experiments. That's why we did these measures. For LED lamps, as I said, and you can see here in this slide, there is a AC circuit, complementary AC circuit behind these circuits, behind these lamps, because we need to control the AC current flowing through these lamps and to do corrections in the power factor. This is the model which is normally used. As I said, it cannot be accurate because they don't consider these AC circuitry behind these lamps. So we did experiments to measure the current and voltage waveforms for CFLs and LEDs. As you can see here, one thing is very obvious here. For CFL lamps, if you look at the current waveform, you can see very sharp points here. It means that we have higher harmonics in CFL lamps. And if you look at the LEDs here, we do have some sharp points, but it's not as sharp as those for CFLs. So it's telling us experimentally that CFLs are generating more harmonics. So they might more effectively affect our transformers efficiency, and because they do generate more harmonics. And you'll see what happens. I'll let you know the latest survey from EIA on how people moved actually in the US houses using CFLs and LEDs. And this slide, you can see the incandescent waveforms, voltage and current waveforms for incandescent lamps and fluorescent lamps. As you can see, in incandescent lamps, because it's only a tungsten filament, because it's a pure resistive load, so we do have, very sinusoidal type of voltage waveforms and current waveforms. When you look at the fluorescent waveforms, the voltage waveform and current waveform, they are getting more triangle shapes other than a sinusoidal wave, but still they don't have very much, sharp points like what we had for CFLs and LEDs. So as we can expect, we don't have any harmonics actually generated from incandescent waveforms, but as I said, they are using 4 to 5 times more wattage to generate the same visible light as LED compared to LEDs. So we have moved from these incandescent lamps that don't generate any harmonics to LED lamps that are energy-saving harmonics, but they do generate harmonics and they do affect the efficiency of transformers. And we have moved from fluorescent lamps towards LEDs and CFLs as well. What the experimental results shows us here is saying that if you look at the CFL harmonics, and we could expect here as well, the fifth harmonic is almost 60% of the first fundamental current. And the third harmonic is about 83% of the first the first harmonic or fundamental current that we are having. So those sharp points that you could see, and if you look at the ninth harmonic here, it's about 41%. The seventh harmonic is about 45%, almost 45% of the fundamental harmonics. So you can see we do have a lot of harmonics generated by CFLs. And if you look at LEDs, it's slightly lower than CFLs, but still we do have third harmonics, which is about 27% of the first harmonic, current harmonic, or for the fundamental current. The fifth harmonic is about 15%, which is much less than what we had for CFL. The seventh harmonic, if you look at the seventh harmonic, ninth harmonic, you can see the 8%, 7% of the fundamental current. So you can see there are CFLs and LEDs are generating harmonics, but CFLs are generating much higher harmonics compared to LEDs. So these are the experimental results that we could achieve from our experiments in the laboratory. There might be some errors in the percentages that we are presenting here, but at the end of the day, the trend is like this. If you look at the incandescent lamp, we have the majority of the actually harmonics belongs to the fundamental current, and the rest of the harmonics are 0.02%, 1%. They are majority of them are less than 1% of the first harmonic. And if you look at the fluorescent harmonics, you can see much lower harmonics like the third harmonic, fifth harmonic, and the odd harmonics are higher than even harmonics. And you can see that here in fluorescent lamps, we do have harmonics, but it's very comparable to incandescent lamps rather than LEDs and CFLs. So now we did a simulation as well. In our simulations, we actually had a 500 kVA in our simulations conducted in Matlab. We had a 500 kVA transformers which converted 20 kV voltage to 400 volt. It was a distribution transformer which fed actually 50 branches of lamps, 10 identical lamps per branch. And then, so we had about 500 lamps, which were demand side and on the transformer. The rated power was 500 kVA. The short circuit impedance was 6%. The cooling was all none, and no load loss was 1000 watt, and no load current was 1.7% of the normal current. And the rated frequency was 50 hertz. So, and we had Z-mit was 0.15, and the voltage, the vector group was DYN5. So in that simulation, what we got from the simulations was like this. We could see that the first harmonic for incandescent lamps was 0.9972 times the nominal current. In fluorescent lamps, it decreased to 0.9939 times the nominal current. In LED lamps, it was actually, it decreased to 0.8457 times the nominal current, where CFL showed the worst case, and it was 0.3 actually times the nominal current. So you can see the maximum permissible transformer current for CFLs when you have pure CFL lamps in our system is much lower than having incandescent lamps, and even much lower than LEDs and fluorescent lamps. What comes to my mind is that the simulations and experimental results are showing us that we need to have a combination of all these four typical types of lamps in our households. What would be the best mix of these lamps depends on the what power system we are talking about. But obviously, incandescent lamps are generating less harmonics, where CFLs are generating the highest amount of harmonics. So when we look at the transformer losses, we calculate transformer losses using the formulae presented in the IEEE standards. You can see that the transformer loss when you're using pure incandescent lamp is 7.8 kilowatt, whereas the transformer loss when using pure fluorescent lamps is 7.857 kilowatt. For LED is 12.4, and for CFL is much higher than the other types of lamps, which is about 100 kilowatt of losses in our transformers. It means that we need to have a higher, a bigger transformer to actually supply electricity to its pure CFL lamps in our households if we use pure CFLs in our systems. So let me just move on to the conclusion and say that what we can do and what are actually the voltage and harmonic levels of various types of lamps were measured in this study. We investigated the effect of different types of lamps on transformer losses. You could see the incandescent lamp was the best, but it wasn't an energy-saving lamp. In terms of harmonics and THD, it was the best, choice. The worst case was for pure CFL in terms of considering the transformer load. It is recommended, in that time, we recommended actually to utilize CFLs in a combination with other types of lamps to decrease the harmonic distortion levels, which could eventually lead to transformer losses reduction. But let me tell you one thing. I didn't give you the figures that EIA published actually in 2020 about the trend and how US people are using CFLs. Amazingly, the CFLs, the usage of CFLs decreased from 32% of homes in 2015 to 12% of homes in 2020. So the authorities in the US were giving signals to the people, to households, saying that CFLs are generating more harmonics and they are affecting our distribution transformers. So they decreased actually the utilizing CFLs in the system, so moving up to LEDs. So as I said, LEDs moved from 4%. The use of LEDs actually in households increased from 4% in 2015 to 47%, whereas the use of CFLs decreased from 32% in 2015 to 12% in 2020. So we do have, at this time that we are giving this presentation to you guys, we do have other types of lamps in the market. They are viable types of lamps. They are energy saving lamps. They help our transformers to operate more efficiently, and they are more recommended, but still all types of new lamps are generating harmonics. When they are generating harmonics, so they are obviously affecting our transformers operation, the efficiency of our transformers, because they are bringing up a condition which is a non-sinusoidal condition, and so they are bringing down the capability of our transformers. So as you could see that as you could see, we in the US, at least in the US, where we do have the survey results, we can see that people are moving from incandescent lamps towards LED lamps. They are decreasing the usage of CFL lamps, as I said, due to the signals that authorities are giving to the people, and there are more incentives that are given to LED lamps. Price signal is a is one of the actually factors which has impacted the usage of LEDs and ESL lamps actually in the US these days. So my part is actually done. I've already presented the simulation results, experimental results, and compared different the effect of different types of lamps on transformer efficiency. I hope that this has been useful actually to you guys, and I'm ready to take on questions if you have any. So you can turn on your microphones and ask your questions, or put in your questions in the chat box so I can see and answer. Yeah, I'm here to take on the questions if you have. Otherwise, I'll hand it over to Lisa to just end this session, if you have any other things to say. The questions are coming up in the chat box for Lisa on how to get the certificate for this course. No worries, Mohammed Hafiz. You are very welcome. How do we consider the effects of harmonics on transformer in such cases? Again, as I said, Derek, the models we have for CFLs, LEDs, various types of lamps are inaccurate. So the best practice would be measuring the current and voltages of these lamps, different types of lamps when they appear in the market. And then what we can do, we can simulate those harmonics and then use the standards formulae to see how they affect our transformers efficiencies. And even the cables, there are some standards on calculating the effect of different lamps and different harmonics levels actually on the cables and their capability. So the best practice would be just doing measurements and simulations, performing simulations to verify the experimental results, and then actually using the formulae used in the presented in different standards. As I said, we do have new versions of international standards available at this stage. If you do have access to these standards, I highly recommend to go through these standards and find, different explanations and what would be the best practice to see what is the effect of different types of not only lamps, but different types of, say, computers, laptops, and how do they generate harmonics, and what is the level of harmonics generated by different types of, products that we're using on a daily basis in our houses. Yes, Kevin. Yes, Kevin. This is one of the major reasons why utilities are reporting transmission losses and distribution losses more accurately. If we want to talk more accurately, they report especially transmission sector losses, which is very important because distribution transformers are more affected by the harmonics generated by end users than transmission transformers. So we are more interested on seeing how different types of digitalized world is affecting our distribution transformers. Yes, we considered the different types of lights in our simulations, 4 types of lamps at that time, which were incandescent lamps, fluorescent lamps, CFLs, and LEDs. Yeah, we didn't consider personal computers, televisions, laptops, mobiles, and different kinds of digital world products. So yes, one person can get involved in research and find out how computers are generating harmonics and what would be the level of harmonics generated by televisions and mobiles in our daily practices. So thanks very much, Hajar Muhyiddin. Any questions for me? Will the increase in the use of LED lamps result in upgrading the ordinary distribution? Yes. Not LEDs. I would say CFLs. were the worst case in our study. And as I mentioned at the end of my presentation, American households has moved from incandescent lamps towards LEDs and ESLs rather than CFLs because they are generating more harmonics and they are affecting distribution transformers. So yeah, moving towards LED is reasonable, but I'm not considering moving towards CFLs as a reasonable movement. So yes, the THD is 100. Some books and journal papers are mentioning THD as well. I didn't mention THD in my study here. The THD would be around 140%. That's right, Zippy. Yeah, when you're talking about 140, just bear in mind that CFL is not the only load for the distribution transformer. We have a combination of loads. We do have steel incandescent lamps, different types of loads. We have to consider the total amount of harmonic levels generated by different types of actually loads we have in our systems, in distribution systems. Lamps are one type of the loads. So we have different types of the loads. To say what sizes, how we should increase the size of transformer in our distribution system, we have to consider all types of loads, not lamps only. Okay. So that wouldn't be a good practice to say that because lamps are generating 140% of THD, so we have to increase the level of distribution transformer by 140%. That wouldn't be correct from engineering point of view. So we have to consider all types of loads that we have in our end users actually use. Some people believe, Kevin, that LED TVs are generating more harmonics too. But some people are saying that because of the AC circuits that we do have behind those LED TVs, they are not the new versions of these LED TVs are not generating too much harmonics because they control the harmonics generated by TVs. So there is a comprehensive study conducted by GE and LEG in Korea. So you can have a look at those studies and see that how much harmonics are generated by new versions of LED TVs. Please look at those studies and the results out there. I recommend to move from, obviously we have to move from traditional incandescent lamps toward LEDs and CFLs. What would be the best mix of lamps in our household depends on what we're using. What is the power system condition that we are connected to. But my recommendation is moving towards LED lamps and ESL lamps rather than CFLs to generate less harmonics and inject less harmonics into our distribution systems. Is that okay? Okay, that was my recommendation actually. LEDs and ESLs are much better than CFLs to be used in our houses or even offices and everywhere that we need lights. Yes, we do have now circuits, Harold, a very good question. We do have now circuits, as I said, behind TVs and different types of lamps. The price is a bit higher. If you buy, that kind of TVs or that kind of lamps, it should be about, the price would be doubled up, but they generate much lower harmonics to what we have. Even the LEDs that are in the market these days in 2023, they generate less harmonic than what we had in 2006 and 7. So LEDs and ESL lamps are my recommendations that we can use in our offices, as I said. No worries, George. It was my honor. And I'm so happy that we had about 130 people attending this session. Okay, I'll hand it over to Lisa because we don't have too much time again to take on questions. You might have my email address to send me emails if you need more information or study results I can share with you, or I can share with Lisa to share with the group. Okay, I'll hand it over to Lisa. We move on to Lisa.
Thank you so much for that
very informative presentation, Dr. Mo. And for everyone, if you want to learn more about electrical engineering or related to electrical engineering, these are our upcoming programs. Maybe you'd be interested. So we have our Advanced Diploma of Electrical and Instrumentation Engineering in Mining that's coming up on, well, the 3rd of April is already closed. But if you have questions about those that are um, starting on the 3rd of April, you can let us know. I'll share contact details later. We can talk about the next intake. And you can also contact a course advisor to discuss your inquiries for these courses. And the next one coming up would be the professional certificate of competency in circuit breakers, switchgear, and power transformers on the 24th of April. And we have a graduate certificate in renewable energy technologies on the 2nd of May, advanced diploma of applied electrical engineering in electrical systems on the 6th of June. And we also have postgraduate programs like grad certs, grad diplomas, and master's degrees on the 26th of June. Undergraduate programs like undergraduate certificates and bachelor's degrees on the 24th of July. And lastly, we have our on-campus bachelor's, master's, and doctorate degrees for our Perth or Melbourne campuses on the 31st of July for our international students. Okay, so I'll just move on to the next slide now. So if you are still interested in attending our upcoming free webinars, we have our computational simulations of wind flow patterns around buildings. And it will be on the 8th of April, Thursday. And sorry, 6th of April. Sorry about that. That's Thursday next week. And we also have the basics of process control and loop tuning. It's a repeat webinar. We ran this before, but we are repeating it due to demand. And that will be on the 19th of April. So that's a Wednesday. And we have the low voltage switchboard design and construction verification. That would be on the 12th of April, and that's also a Wednesday, right? And if you would like to request for your certificate of attendance, we give it for free. I will just paste this link here in our chat box so that everyone can access it. Or you can also use the QR code. If you find it challenging to do, just use the link instead. That's fine. Okay, hold on. I'm just paste it here real quick. All right, I sent the link to our chat box here for everyone to copy and paste on your browser. You can request as early as now. Usually our deadline for requesting the certificate would be by Sunday, end of day this week, and we will be sending that to you through email in 1 to 2 business days. All right, and since we're done with our Q&A, let's just skip that part. And thank you so much, guys, for attending. You may visit our website. That's www.eit.edu.au, and there's our office address there for those who'd like to visit our office in Australia. Our phone numbers for those who'd like to call, and you can also send an email to webinars@eit.edu.au for those who have questions about webinars and concerns about the video recording and accessing the PDF copy or your certificates. And you can also go to www.eit.edu.au/schedule to see our list of courses that are still going to have an intake date within the year. And that's it.
Thank you very much, everyone.
Thank you so much, Dr. Mo. Thank you, everyone.
Thank you, Lisa.
Have a
That
great
was a
day.
great experience with you. Have a great time there. I just stop recording.
Likewise.
Bye.
All right.